So today, last lecture this semester, one of my last lectures, and it's the end of our three-part series on image generation, right? And so diffusion models. So far, as far as image generation has gone, we've covered variational autoencoders and generative adversarial networks, or GANs, right? So before we kind of go back into the architectures and what are diffusion models, I want to do like a review of kind of like how to conceptualize image generation, right? So again, when we talk about image generation, we're working in what's called the image space, right? So this is the domain of all possible images. So remember with ML, we have features, right? Another term for features like a dimension, right? So for example, if you have three features, well, you could plot those on a three-dimensional axis. Sorry. Does that make sense? So again, like you could kind of plot your data points in that 3D point. So you can imagine the more dimensions you have, the larger your space is, and the harder it is to keep track of things, right? Like how do you optimize a function in like 1,000 dimensional space? So the image space, you can think of every RGB value, right, is its own feature. So therefore its own dimension, right? And when I see like each R, like R is a dimension, G is a dimension, B is a dimension, right? So if you have a 10 by 24 colored image, that's over 3 million dimensions, right? Like we have no way of feasibly plotting that ever, like on a coordinate plane, right? So you could imagine if we were to try directly work with images, we'd be forced to work in a very high dimensional space, which we don't want. Does anyone remember why? What's bad about working in extremely high dimensional space? A couple things. Recursive dimensionality, thank you. The other thing is if we directly work with image on the pixel level, we lose the spatial information, don't we, right? That's kind of from CNN lecture. Um, so again, regardless though, when we're talking about generating images, we want to generate images, right? We don't want like most of this image space, so the domain of all possible images, you can imagine it's mostly noise. Like if I randomly choose like if I randomly sample an image, so randomly pick RGB values, I'll probably get something like this white noise in the background. It's very unlikely that if I sample it from image space, I'll get like this nice picture of a cat. Very like slim to none, right? So I just for learning purposes, I've tried to visualize image space as like this two-dimensional construct, but in reality, we're working with like millions of dimensions, right? But regardless, if we want to generate images of cats, we want that section of image, this very sparse section of image space, right? So generally, when we're talking about these spaces, we think of probabilities, right? So we want our model, right, to have positive probabilities on like, you know, areas of the image space that are in blue, right? So in other words, any image of a cat, like there's 2 points there, we want our model to have a positive probability. So if we're thinking about a data sets, right? Like if we treat a data set as a probability function, right? Any image in that data set has a positive probability, right? Like there's a positive probability of um, that image, right? In our data set. Um, and so what we want is when we're generating images, we want our generative model, so P theta, right? Theta being weights and biases. We want our model to look like this probability distribution of our data set. And so if we can approximate our data set distribution with our model, that means we've done a pretty good job, right? Um, okay. So again, as I said, image space is like way too big. It's like basically impossible to optimize directly in it, or it's very difficult. So what we have instead, what we covered in GANs and in various autoencoders, is this thing called latent space. So latent space is just a fancy way of saying a significantly smaller dimensional space, right? Not as small as 3 dimensionals usually, but like, maybe like under 50 or way less than 3 million, right? And so a common strategy, right, is we take images from image space, right? And then we learn a mapping between the subset of images that I want. So like ICAT, the subset of images, cat images in image space, and we learn to map them in latent space. So why do we bother doing this? Well, if we want to create a new image, instead of like randomly trying to sample something from a three-dimensional plane, right? We can easily sample something from latent space, where all cat pictures are clustered together in this like roughly this circle space, right? Again, if you have an untrained neural network, you can imagine that like each like this one-to-one mapping is like, the embeddings are not close together. The vectors in lane space are not close together. So the goal of training is to make sure our latent space is well organized, similar images are clustered together, right? So this framework is exactly what variational autoencoders did, right? So again, they would take images from image space, right? And learn how to plot them onto latent space. So this lower dimensional space, right? So before training, right? You can see that like, in latent space, these images are basically mapped to like random vectors that are not nearby each other, right? And the goal of training is to almost shape this latent space such that the images that we want are nearby each other. And if you want to create a new image, then we could just sample a new point. So like, that blue dot, and then hopefully that points back to a new image in image space. So again, it's we're directly learning the probability distribution P, right? So with GANs, though, they take a different approach to this latent space dynamic. What they instead do is they start with a latent space with a bunch of vectors close together, right? So if you remember, with GANs, we sample vectors from the normal distribution, right? So vectors are around like roughly like -5 to 0 for each of their, or sorry, -5 to 5 roughly for each of their values, right? So again, all those numbers are fairly close to each other. And then for each of those random lane vectors, we learn to map them to image space, right? So we start with our latent space vectors already close together, and then, but they point to noise in image space. And we're basically teaching them to point to like the subset of images that we want. So with VAEs, we go from image space to latent space, and we want to create a new image. We take a latent space vector and blow that up, right? With GANs, we start with latent space vectors and we learn to map them where we want in image space, right? And then again, similarly, to create a new image, we sample a image or a vector from latent space, and then boom, we get hopefully something that looks like the images in image space, right? Is that kind of conceptual overview, like, does that make sense? Okay. So, GANs kind of do something, or sorry, um, yeah, actually, we don't have to talk too much about GANs. Diffusion models do something that's unintuitive, at least in this point, right? I know how we said like navigating image space is very difficult. So, or sorry, like sampling something in image space is very difficult, right? So instead, they kind of rephrase this problem as they start in like the original GAN or diffusion paper doesn't work with latent space. They start somewhere in image space and they learn how to navigate to the subset of image space. So like this blue region, right, that we want. So they're basically learning mappings, like pathways in image space. Whereas GANs and variational autoencoders are learning, like they have latent space, image space, they're learning some kind of mapping, right? Diffusion models learn to navigate image space, right? So as of now, no latent space. Does that make sense? And so, okay, how exactly do they do this, right? Because image space is really high dimensions, really hard, right? So what they do, diffusion models have two steps, right? First, they go through their data set, and for each image, they find a pathway from like dog space in this case, like the subset of images that are in our data set. So think of dogs in this case, a data set of dogs. And they incrementally add noise until you leave dog space, right? And so when I say noise, I mean like this, like, the stuff you see on a television screen, right? Like absolute garbled pixels, right? And so if you kind of look at the pathway, we're iteratively slowly adding noise until, at this point, like it's almost kind of like a dog, not quite, until we leave dog space, right? And so that's the first step of diffusion, learning the pathways to leave image space, or sorry, dog space, I guess. And then denoising is, okay, we have that pathway. It's training a model to walk your steps back effectively, right? So this original pathway of leaving dog space is kind of a ground truth. And then reversing that pathway is the goal of diffusion. We call this denoising, right? So again, the idea is, okay, can I sample a random piece of noise in this larger image space and then learn a pathway to go back to dog space? Okay, right. So again, there's two steps. As I just said, noising, where you start with a clear image and you gradually, incrementally add Gaussian noise to it, right? Again, you can imagine like each time you add Gaussian noise, you move in the image space. That's like like a high dimensional step you take, right? Denoising, again, also you subtract noise, you're moving back into dog space or your data set subspace and image space. Okay, I've been talking a lot. Any questions about like this whole image space thing, GANs, variational autoencoders, or diffusion? Just like conceptual stuff. All right, good. Nice. Okay, so before we talk about how this mechanism actually works, right? You guys need a little bit of background just to understand the operations. So what does it mean to sample noise from like a normal distribution? I said this briefly, but essentially what we're doing, oh shoot, I thought I was just sharing screen. Okay. Essentially what we're doing is that we I don't want my face. All right, okay, my face is there, I guess. Okay. Uh, basically, for each pixel, well, we just randomly select a value um, from like the normal distribution, right? Um, so we can pick where this normal distribution is centered, right? It doesn't really matter too much. Usually we do a standard normal distribution. And of course, you might say, hey, like RGB values are from 0 to 255. But then we could easily just have a mapping, right? Like we could just say, hey, like the lower bound, like let's say like around -5 maps to 0, +5 maps to roughly like 255, right? You can just have some arbitrary mapping, right? But that's kind of how you sample images from normal distribution. Does that make sense? Every single RGB value, just randomly pick a number. Oh, sorry, not randomly. Sample from the normal distribution. Okay, so here's the actual architecture, right? So so if you remember like the graphic I had earlier, right? Um, the actual machine learning, like the learning happens in predicting like how to go back into image space, right? So noising is just a straightforward process. You just sample Gaussian noise, add it to the image, and just keep doing that. There's no learning involved. It's like literally add two images together, right? Denoising is the process of predict. So you have a noisy image, you predict how much noise is in that image. So in theory, right, if you predict how much of this image is noise, you can just subtract that out and get the original image, right? So that's what a diffusion neural network does. It takes a noisy image and it predicts the amount of noise in that image, right? So again, if the input image is like height by width, right? Like 1020 by 1028, the output is 1020 by 1028, right? And each pixel value represents the amount of noise, right? And so this structure here is, if you were here for autoencoders, it should look somewhat familiar. It's a encoder decoder structure, right? So we haven't covered ResNet. I'm going to do that in just a sec. But essentially, ResNet blocks, you can think of them as like CNNs, max pooling layers, right? Or sorry, convolutions, max pooling. Basically, looking at the spatial information and then shrinking the image with max pooling, right? And then you keep doing that. So you keep shrinking the image until you get that smaller latent representation. And then you blow that back up, you upscale, right, into figuring out how much noise you had. Yeah. And so I'm going to cover some of like what residuals are and what positional encodings are right now. Okay. So so again, this is just like a general neural network, right? I'm just talking about like a general, whatever structure we want neural network, right? So let the first, like some terminology, let the first image we have, like the original image be X naught, like the input, and the final output be X of L, right? And so kind of as we pass through the neural network, each layer, the output of each layer, like call it like X1, X2, X3. So like the output of layer 3 is X3, right? So we have these intermediate values, right? So again, you can think of like the operation of the neural network. So calling each layer, right? Just think of that as like a bunch of functions being called on, well, each input, right? So for example, like layer 1, well, that's some function F1 operating on an image, and the output of that, oops, sorry, is called by F2, by F3, and so on and so forth, right? So does that make sense? I'm just like kind of giving you some terminology. Okay, great. So then the intuition is then like, what are gradients in this case? So remember, when we back problem this, we're going to have the gradient for each intermediary value, right? So what is the gradient of X naught with respect to XL mean intuitively? Well, that means, okay, um, how changing X naught, so how a change of the input image impacts what the output looks like, right? Well, what does XL over XL minus 1 mean in that case, right? Well, that means how layer I's input affects its output. So in other words, the change some layer had on its output. Does that make sense? So that's what gradients mean in this case, right? Like how each layer changes its input. transforms input, right? So, okay, so yeah, I just said what that is. So when we're doing like back propagation at some point, we will have to calculate the gradient of our output with respect to the input at some point, right? When we're doing this long ass back propagation, right? When we do this chain rule eventually, right? And so, you can imagine that like a lot of diffusion models, especially in new architecture, they're very deep, right? And so we run the risk of if you guys remember normalization, right? Like we want our outputs and therefore gradients to be not too big, right? So if too many of our gradients are, well, if we have like 100 layers, right? And most of our gradients are below one, right? Like less than one. Well, what's anything less than one raised to like a large power? Zero, right? Like for example, like 0 point, like let's say all of our gradients for whatever reason are less than 0.95, right? Well, if we have a bunch of layers, that converges to zero, which means we have a vanishing gradient. It's very problematic, right? Because you know, this is more prominence in these kind of image to image generation tasks. Because again, what do these layers, what does the gradient of a layer mean, right? Well, remember the gradient of a layer is basically how much that layer has changed its output, right? So gradient of XL with respect to XL minus one is how much did layer L modify the image? Well, if a layer didn't really make much of an impact, remember like with really deep neural networks, a lot of the layers just might not do much, right? They might just not have much of an impact. So if enough layers just have little to no impact, so in other words, the gradient is near zero, the entire back propagation is cooked, right? Like if one gradient is almost zero or zero, so in other words, one layer doesn't change its inputs, boom, vanishing gradient. And if most of the layers make very small incremental changes to their input, also vanishing gradient, right? Because those gradients are less than one, right? So what's an easier solution for this, right? Oh, sorry, I skipped a slide. So what we're effectively doing, if you remember that function representation, is each XL, so like XL plus one being the output after layer one, like it's some function, right, of XL, the previous inputs, and the weights, right? It's some function. What residual connections do is they rephrase this as the next layer, like the the next intermediate value, right, is a sum, right? It's not just some function, right? It's a sum of the inputs plus whatever changes we made to the input. So it's an additive change, right? So this is pretty significant, right? Because we're now learning the difference between the inputs and the outputs, right? So why does this distinction matter, right? Um, well, now the gradient is at least the identity matrix. So in other words, it's at least one, right? So in other words, if some layer L makes no changes, right? Or sorry, let me go back a second. Let me just explain this graphic because you see this kind of graphic a lot with residual connections. Essentially, what you're doing is before we pass whatever value into the next layer, we pass the original image through our layer, our neural network activation, or sorry, our weights biases activation, right? Whatever steps we want to do to it. But then before passing that modified matrix, we add that value, so this modified value, with our original image, with our original inputs, right? And then we send to the next layer. So that's why it's additive. Does that make sense? Does that make sense? Okay, good. So again, if this layer does nothing, right? Then the gradient of that nothing operation is just the identity matrix, right? And that's, if you multiply something by one in our back propagation, nothing, like we don't have a vanishing gradient. Nothing happens, right? If we do make a change, then it's what our gradient would have been, right? If we didn't do this additive operation, right? Is that kind of clear? So like again, like for example, like so we've kind of rewritten our operation as like a sum, right? So what is the gradient of x of L with respect to x of L? One or the identity matrix, right? Again, because we're working matrices, it doesn't reduce to one, it reduces to a matrix acting as one, right? And then if this F term, the transformation, does nothing, that boils down to a zero matrix, right? I plus zero equals I. So originally we would have just had straight zeros. Now we have straight ones, or diagonally ones, but that's the point. So in almost any deep neural network you see in the modern day, almost all of them have this residual connection because now we have able to have really, really deep neural networks without vanishing gradients, You still can, but this makes it very robust against vanishing gradients, right? Um, yeah. So almost all the architecture we'll cover in the future, like have some form of residuals. Okay, any questions about residuals? All right, great. The other thing that we have are something called positional encodings. So essentially, remember, we're kind of navigating a path through image space, right? So it's pretty important to know which step in the path you are. For example, if you're really deep in that noisy area, very far away from like that set you want dog space or cat space, right? You might want to take bigger steps, right? Because you're early on in the denoising process. Whereas if you're very close to dog space or image space, you might want to take smaller steps because you're almost there, right? So knowing where you are, like which iteration or which step you're on in denoising is very important, right? So how do we incorporate that information into our neural network? Right now, we just take an image and we just predict the noise. We have no idea which step we're on. So we have something called positional encodings, right? So it's basically a vector representing a time step. So every single time step, like one, or I guess 0, 1, 2, 3, 4, all those are assigned to some d-dimensional embedding, right? And so for each dimension, this is kind of the value you get out. What is that, right? But notice that this is a sign, right? That's important. Um, so I had this like kind of this visual over here, right? So you guys it's kind of small. Do you guys see like these distinct colors? So imagine we have one, two, three, four, five, six separate like or sorry, we want to figure out the encodings for like position 1, position 2, position 3, and so on and so forth, right? So remember, each of these numbers are being mapped to a dimension, or sorry, to a vector, right? And each of these colors represent a separate vector at the same dimension. So right now, we're showing at dimension 1 what all the values would be for like these 6 distinct vectors. Does that make sense? So like d equals 2 is like what um, the element in the second index for like each of these 6 vectors, right? So in the early dimensions, right, notice that all of these are basically the same, right? Like in the first like dimension, they all have very similar values, right? As we keep upping the dimension numbers, like the index number, sorry, should probably zoom in a little bit. Yeah. So I have up to 20. So dimension 1 to 20, right? So I don't know how to make them bigger. As we keep upping the dimension count, notice that farther values start to deviate a little bit earlier, right? So again, if you were to just look at the first 5 dimensions of a positional encoding, right? You would be able to tell relatively that, hey, like for the first 5 values, these numbers were all roughly the same, right? Whereas this number farther out was way more on the 5th dimension, farther out than these first 4 were, right? Like even on the 10th, like on the 10th dimension, for example, right? So like as I increase the dimension count, you can see that the curve looks more and more like sinusoidal. Like it looks more and more like the amplitude of the sine function is shrinking, right? And so what this does is that in later dimensions, right? Like later indexes of our array, um, we get like we see like sorry, the distance between close by points are exaggerated, right? So in other words, the whole point of these positional encodings is to figure out like how do we distinguish between nearby and far by like points, right? So again, at a dimension of 10, right? So like from indexes like 1 through 10 or 0 through 9, I guess, right? Low like nearby points all have very similar values, right? Whereas far by points, you can see like they have very different values, right? So even if you didn't know like the positional numbers of these, like, oh, you didn't know that this was a 1, this was a 2, so on and so forth. If you just look at like the value at dimension 15, you could be like, okay, like I could see this negative number and these positive numbers and tell that this negative number is like further away, right? And as we increase the dimensionality count, we get more and more like granular sine functions, right? Until even like nearby points are separated, right? So like I dimension like 100, right? Even nearby points like have very different values. Does that sort of make sense? So in lower dimensions, nearby points have very similar values. So like the lower the dimension, the easier it is to separate large values from small or like far apart values. the more you up the dimension count, the more granular you get, the easier it is to separate nearby values, right? And so, you know, if you're training a neural network, right, and you want it to kind of understand which you give this sorry, this positional encoding, and you want to say, okay, what step am I on, right? The model could pretty easily figure out to just look at the dimensions, right, and see when they diverge, right? Okay. So for example, you see positional encodings very often in images, right? So like sorry, text, not images. Like oftentimes you want to encode the position of a word where it is in a sentence, right? So here I kind of have the encoding for the word bird, right? Again, it's independent of the word itself. It's just based off of its position, right? So if you look at this in isolation, this doesn't really mean much. But if you look at the encoding for the next word, right? So the next position, um, the values in the first really like, oh, sorry, the first three dimensions are very similar. Dimensions four and onward become more exaggerated, right? So model could be like, okay, these two values diverge at dimension four, they're probably close together. Whereas, oh, these two values diverge at like dimension like one, they're very far apart. Does that make sense? All right. So I think I've been talking about positional encoding a little bit too much, but I just want to make sure that's clear. So again, the architecture of like this kind of encoder decoder architecture that we use in diffusion models, we call it a unit. What makes it a unit is again we use these residual blocks, and we positional encoding is not specifically units, but that's another thing we do. And again, when we see residual blocks, that just means we're doing these convolutions, normalizations, sometimes max pooling, but they have these residual connections, right? So in this case, right, in our example before, we had residual connections like wherever we wanted. In this case, we have a residual connection between, honestly, it's easier to see in the earlier slide. Yeah, we have residual connections between like corresponding spots in upscaling, in descaling and upscaling, right? So for example, like the first block has a residual connection to the last block, right? The second block has a connection to the second to last block, right? Why are we doing that? Like, why would we, have those specific connections? Well, that's because remember, the goal here is to downscale. The goal here is to upscale, right? So in upscaling, it helps a lot to see what the original image at that dimension looked like, right? So that's kind of the rough intuition for residual connections. Okay, yeah, that's pretty much it. We haven't really talked about diffusion models at this point. Okay, now on to the actual diffusion stuff. Unfortunately, it's a lot of math. But remember, so let's start at this top equation over here, right? Remember, x's represent images, right? So we start from xt minus 1. So this is like, um, so from xt minus 1 to x of t, in our noising step, we want to add some increment of noise, right? So let epsilon be like that noise image, right? So if our image is 10 by 24, epsilon is 10 by 24 of just noise, right? So as we incrementally add noise, we want to do it gradually, right? So we take our previous image, xt minus 1, right? Um, we set some parameter beta between 0 and 1, right? Let's say beta is really small, right? Beta is like 0.1, right? That means we retain square root of 90% of original image. And then we add in, right, square root of 0.1%, or sorry, square root of 0.1 amount of noise, right? So the the lower beta is, the more we retain of the original image, the slower we add noise. Does that make sense? Okay, this is just a function for adding noise. In the equations, I have like this alpha term that's just 1 minus beta. It's just 1 minus beta. It's just like annoying to write out. It gets a little bit confusing writing out 1 minus beta all the time, so I just kind of took that out. So essentially, right now, this is kind of a recursive algorithm, right? As in like, we know how to go from one step to the next step. But how do we go from like x0 to like x 1,000, right? Without doing all this iteration, right? Because otherwise we have to run some kind of for loop, which is slow, right? So essentially, um, let's say we want to go from like X1 to, from X0, our original image, to a slightly more noisy version X1, right? Well, it's that equation above, right? What happens if we want to go from X1 to X2? Well, we just substitute in the value of X1 where, yeah, we just substitute in this equation for where X1 is, right? As we do these substitutions, notice that we have like, we're just multiplying these alpha terms a bunch, right? And we're adding a bunch of like epsilons with coefficients, right? So if we simplify this, it boils down to this equation, right? So going from x naught to let's say like x3 is square root of each, alpha three times, right? Plus square root of alpha 3 times alpha 2 and so on and so forth, right? So in other words, you can boil that down to this looks bad, pretty simple equation over here, right? So this first term, right, is just the square roots of all the alphas you have. And again, if alpha is a constant, then it's just that constant raised to that, right? Later on, we see that alpha is usually not a constant, but if it's a constant, it's just a number raised to a power square root. Square root goes away, right? So really just a constant times x naught plus this ugly summation here, right? Well, this really just boils down to 1 minus alpha hats, right? So really it's just the square root of some parameter, right? Plus 1 minus the square root of some parameter times epsilon. So we've almost gone back to this original form, right? We just have to make sure that, hey, this alpha hat is just like a bunch of values multiplied together, right? Yeah. So again, the top form is the recursive form of like the denoising process. The bottom equation is the denoising form. Or sorry, not that denoising form. Like the kind of the functional form, like going from x naught to xt, right? Does that make sense? Yeah. And so again, conceptually, like visually, this is what we're doing, right? So if this is our original image, we're taking some percentage of it, adding the remaining percentage in noise, and then this is what we get. So if alpha is really high, 0.9, that means we retained most of our original image. We only added a little bit noise. If alpha is really low, that means most of our image is now noise because we added a bunch of noise. Again, keep in mind we're working with percentages, right? So like we might take away like 90% of the image and add 10% noise, right? That kind of percentage thinking just helps the math be a lot cleaner. Okay. So the other thing, so as I said earlier, usually alpha and beta are not just like they're not just constants, right? So usually we use something called a scheduler to kind of modify their values as we kind of do the denoising process, or sorry, the noising process, right? So here I kind of have like what it looks like to linearly decrease or linearly like drop alpha versus like using this cosine function to drop alpha, right? So you can see with linear, almost counterintuitively, like we enter like the image becomes super noisy like very early, like almost halfway into the noising process. Whereas using this cosine strategy, we could still almost make out the dog like very late into noising, right? So why do we care, right? But the problem is, remember, we still want to denoise. Like the next step is denoising, right? If our dog becomes just straight garbage too early on, right? That makes our pathway like the last half of our pathway garbage. Like this last half of it, really the last third of the pathway is just straight noise. There's nothing useful to gain from here. Versus if we kind of slow down the noising process at the end a little bit more, sorry, if we slow it down a little bit more in the beginning, we have more time to like go from, we have more variations of noise to work with. Like we lose less information quickly. Does that make sense? So generally with the scheduler, we work with this cosine function. I know it looks really hairy, but it's essentially like adding essentially we're adding a lot of noise like slow. We're adding noise slower than we are linearly at the end. In the middle, we add a lot of noise fairly quickly, but at the end, we slow down, right? Again, this is to prevent losing information too quickly. Okay. Any questions about noising?
Uh, So wouldn't the cosine add, it would add more space early on compared to linear, right?
Sort of. It adds the most noise in this middle part. Like if you just think about the derivative, I'm sorry, the derivative, right? At the beginning and end, the derivative is really low, right? Like we add a little bit of noise. Again, the reasoning being that like if you kind of think about denoising, right? At the end, we want to experiment with images with a little bit of noise to get like fine grained detail. Like in other words, like a little bit of noise means like we're taking small baby steps, right? Yeah. Around this middle is when we start amping up the noise because like, this image to this image, like I can't tell the difference, right? Um,
Just like you're creating the foundation by the middle and then you're adding the finer details.
yeah,
That's why it slows down.
yeah.
Does that mean for denoising you want to use time?
Hmm?
Does that mean that for denoising you want to use time?
Sine. We're using cosine, but like if you could rewrite this as like a sine function.
For
Yeah.
denoising.
Yeah. Or for
For
yes.
denoising.
Yeah. For like again, look, what this refers to again is like the coefficient of alpha, right? Which means how much noise to add at a given step. Does that answer your question?
Yeah, so like when you're going in the opposite direction, like when you're um taking like the noise out, would you want to do
Oh yeah, so that's independent of so far we haven't actually covered much learning or like training in the sense, right? This is just a strategy in which like we have a very controlled, slow way of adding noise, right? When we're going backwards, there's no cosine, none of that. It's just neural networks, just predicting the amount of noise in a given image, right? This cosine stuff, linear stuff is specific to noising. Just like make sure we don't add too much noise quickly, right? Yeah, good questions. Okay, so denoising, right? So naively, right? You might ask why. So if you remember with denoising, right? We have a noisy image, we predict the amount of noise, and the prediction of noise is the deep part, and then we subtract that noise non-deeply, I suppose, right? So why couldn't you just, given a noisy image, right? Predicts the denoised part, or um like uh if we have a noise image at time step 1,000, right? Why don't we just predict the denoised image at time 1,000, like 999, right? Or why do we have to do like this predict the noise middleman kind of thing, right? So again, here at the bottom, I've just kind of rewritten this equation as like expressing the denoised image, slightly denoised image in terms of the outputs, the noised image. Again, same function. I've just like kind of rearranged the terms, if that makes sense, right? Um, yeah. So again, in a neural network, we're predicting this epsilon term, but why don't we just kind of do this, right? Um, so there's a couple of reasons. One, for machine learning aside, this would force us to store the entire path. Like if we take like 1,000 or like 2,000 steps, that requires us to store like that many images, noisy images, and that amount of noise that was added incrementally, right? So if we have 2,000 steps in our diffusion process, then we have to store 4,000 images, right, for a single image in our data sets. So if our data set is like, hundreds of thousands of images large, that's going to increase by like double, right? Or sorry, by a factor of 4,000, right? So just from a hardware perspective, this is not preferable, right? Um, okay. Uh, yeah. Um, the other thing, right, is that um like the difference between images, especially like when they're full of noise, is just really small. Like, can you tell the difference between these two images? There's like this is literally like basically the same image, right? They're like very incrementally different, right? And as you remember, if we have small differences, right, between inputs and outputs, that means we have a small gradient, vanishing gradient. We don't want that, right? So this is more of the fundamental reason as to why um, we don't want to directly predict slightly denoised images. So that's why predicting the difference, right, is just an easier problem, right? Because again, you could visually see that like this way the gradients are less likely to vanish, and we don't have to store the entire history of images and like image noise pairs, right? Again, this just boils down to this being an easier problem, both the hardware side and vanishing gradient prevention side. Okay. So when we do this, right? Again, so I'm explaining why we don't predict like this intermediary E of t noise value, like the amount of noise we add in a single time step. Instead, we predict from time step 2000 how much noise was added to the original image, sorry, right? So instead of learning like this intermediary value, right? Like, like from this dot to this dot, like this amount of noise, right? We try to predict the amount of noise from here to here, right? And again, that's really just to reiterate, that's really because like these two images have almost no visible differences, right? We're going to have a very small gradient, right? Vanishing gradient. We don't want that. Whereas these two images are very visually different, right? We're going to have a very strong training signal, a very strong gradients. Does that make sense? Right? So let's kind of visualize this, right? If we start from X, so okay, we're denoising, right? We start with the noisiest image we have, noisiest, just straight garbage, right? We predict this epsilon value, the amount of noise that was added to the original image, right? So, we predicted this thing, right? So if we subtract this E theta, the predicted noise, from X2000, we might like, it's not going to look like the original image, right? It's probably going to look like something pretty jumbled up, pretty distorted, right? The key here, that's fine though, because we just want to move, right, in the general direction of dog space, in the general direction of X naught, right? So we take a small step in that direction. And when I say a small step, I mean subtracting a small amount of this noise, right, from X2000, right? So, okay, now we're at X1900. We've taken a bunch of steps. Once again, we predict how much noise was added from the original image to where we are now, right? As you can see, like as the image gets slightly more and more clear, um, we get better approximations like that point towards the original image, if that makes sense. So again, every single time, like every single step, we try to point to X naught. We do our best point at X naught, right? As long as we keep doing that, we'll eventually, right, like X 5000 when like, sorry, this is not the right image, but at X 5000, right? Um, when the dog is mostly visible, like, there's enough information for us to point towards X naught. Okay, is that clear? Like the intuition behind this? Okay. So, back to kind of our formulas. What is the formula for like the noise from X naught to X of t, right? Because again, we want to predict xt minus one, right? Based off of the noise from X naught to X of t, right? So again, we start with our recursive equation, right, from xt minus 1 to x of t. Um, and then we have our other equation of x going straight from x naught to x of t, right? So we have a recursive equation and from x naught to x of t, right? If you just substitute terms, you end up with this guy down below. So this is essentially like in terms of the noise from x, so from the x naught, the original image, to our current image, right? That noise, um, and this randomly sampled vectors. So in other words, um, we can predict, like, we can go to the next denoised image just from the current noisy image that we're at, right? Our input image, and our prediction of noise from the original image to x of t, right? And then we have this extra term over here, and I'll get to that in just a second. But this first term is kind of what we've been talking about. Any questions about this math? Perfect. So you might notice that we have an epsilon over here, literally a random epsilon. And the whole point is we're denoising, right? So that's kind of why you see that subtraction sign over here, right? Why are we adding noise again, right, when we're denoising? Is that kind of counterintuitive? Notice we're also using this new beta term instead of this alpha, or sorry, that's not, say beta term. Again, so this red equation is what we've been talking about, right? So we predict the amount of like some amount of noise and we subtract it from our noisy thing to go to a less noisy thing, right? Um, Now this beta term though is we add a little bit amount of noise. Now we want to add a very small amounts to almost deviate our pathway. Remember we have these pathways. Adding this random, like almost like this random direction change, right? Why do we do that? Well, remember the whole point is to learn pathways, right? Like I want on inference, right, to pick a random thing in image space, this random noise vector, and then have it point back to dog space, right? So I want to learn as many pathways as I can. If I just learn the exact same pathway, like, the path that, remember, we have a path from dog to noise, right? If I just learn the dog to noise, noise to dog, that one pathway, right? Then what happens if I sample a different thing of noise, right? Or I start somewhere else in my image space, right? So by having this epsilon term, it forces us to go stochastically. In other words, it forces us to take a different path each time. And that's kind of the key here. By forcing us to take a path, a slightly different path each time, that's still in the rough general direction, we explore more of this image space. So our model becomes more robust. That's the main reason. Does that make sense? So that's why even while denoising, we add a little bit of noise. So we have all these like green different pathways. Okay. So finally, we're finally at our loss function, right? Remember, I'm saying all of this, but really at a given inputs, a given noisy image, our output is predicting the amount of noise we had, right? So training our model is pretty simple, right? Um, we effectively just calculate a mean squared error between the noise you predicted, E theta, and the actual noise from, remember, the noising step. We have that, right? The noising step amount of noise. And we just calculate mean squared error. Super simple. If you remember from GANs, I mean, we were solving like two competing loss functions, a min-max problem. That's just like a nightmare to train, right? This is just a nice, beautiful mean squared error. We've seen this, a ton of times in the past. Okay. The key here though, is, remember like our pathway might be like 2,000 steps long, right? We might have like thousands of images, right? So that's 2,000 times 1,000 images, right? That's how many inferences we need to make times the number of epochs, right? You can imagine training would take forever, right? So to kind of be a little bit more efficient with our training, what it kind of turns out is that we just randomly pick like a position in one of our paths. We just randomly pick a position, right? And then we predict what the direction should be from that random position, right? So instead of like literally learning every single path, we just randomly pick a point in a known path and then predict, okay, which way should I go, right? So again, that's a more efficient way as opposed to just going through all 2,000 steps. Does that make sense? Okay. Again, the researchers tested this method of like choosing, like out of 2,000 steps, like randomly sampling 500 or like 100, as opposed to testing all 2,000 steps, right? And they found that like both work the same way, like just as well. The sampling method is just way faster. Okay. So again, just to illustrate this, right? The input to our UNet, our diffusion model, is a noisy image, right? And our time step. Remember, the time step is just used so we can like have our positional encodings, right? So we predict this E theta. E theta is the amount of noise that we think from 0 to 55. So all this accumulated noise is what we think E theta is, right? And our loss is well, the actual amount of accumulated noise, epsilon, the mean squared error between epsilon, actual amount of accumulated noise, and our prediction. Okay, that's really the key thing. Any questions about this? Like that's like the main thing. Okay, and I just explained this algorithm, right? But once again, we sample like some no noise, an image from our data set, right? Again, no noise has been added, X naught, right? Um, we pick a random point on one of our pathways, right? Again, our noising pathway, right? So from original image to straight noise, we pick a random point on that pathway, right? We pick, some amount of noise, right? And then, we add that noise to our image, right? And then we try to see how much, we predict how much noise is actually added. We know how much noise is added, mean squared error between those two, right? And you just keep doing that until the model converges. Okay. So now I'm going to talk a little bit about some improvements to diffusion models, right? If you remember all the way back at the beginning of this lecture, I said how annoying it is to like how difficult it is to navigate image space, right? So again, um, or sorry, sample from image space, right? Diffusion models are all about navigating image space, but still it's hard to navigate a high dimensional space. So a very quick improvement upon diffusion models is called latent diffusion models, LDMs, right? Very simple, same concept. It's just we take our image space image, train some kind of encoder, autoencoder to take an image to latent space, the same latent space in GANs and VAEs. We do the exact same diffusion steps, right? Noising, denoising, right? Or sorry, we do the denoising steps in latent space, right? So we're predicting the amount of noise that was added, but to latent vectors, like these small dimensional vectors, right? And then once we enter the latent space that corresponds to like the part in latent space that corresponds to dog space, right? We just chuck this latent vector back into our decoder, and then boom, we get our dog, right? So essentially, because latent space is so much smaller than image space, we can have shorter pathways. So this would just work much, much faster than navigating this massive image space. Does that make sense? Okay. Again, like the loss functions are literally the same, right? It's just instead of predicting the amount of noise that was added to an image, we predict the amount of noise added to some smaller dimensional vector, z of t. That's the only difference. And we just talked about autoencoders. And so yeah, so GANs, VAs, diffusion, there's a bunch of text. Generally, just really quickly, diffusion is the state of the arts, right? Why is that? GANs, especially 2020 and before, they performed really good, like very well, right? Because their whole paradigm of like um, producing an image and then being like, hey, is this an image or not, right? That worked really well, right? VAEs perform the worst, right? Because they reconstruct an image and they do the mean squared error at the pixel level, right? Of like, here's my predicted image, here's a real image, mean squared error, right? What the models would figure out and converge to is like just having a very blurry image. Like a blurry image and the original image have a very low mean squared error, right? I hope that kind of makes a little bit sense why, right? Like a blurry image is just like, the numbers of each pixel are like slightly off, right? They're like averaged together. So VAEs would be very easy to train, but would be blurry and like pretty bad looking. GANs would have, because this guess and check method was really effective, they look really well, but it was hard to make them like train them on large data sets because of that min-max problem. It's like really hard to train these two models concurrently. Diffusion models, um, like VAEs, they have a very simple loss function, just mean squared error, but on noise, not on raw images, big difference. Um, and we learned like ants, like they produce really high quality images. So easy, objective, but also high quality. So post 2021, diffusion models have been like the state of the arts. GANs are still pretty competitive in some regards, but diffusion models are easier. We have a few more minutes. So I'll just like talk a little bit more, but the 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 algorithm I've described today is called DDPM, denoising diffusion probabilistic models. Yes. um, you don't have to just DDPM is like, that'll show up on Google. Essentially, what we're doing is like this is a very early version of diffusion, like the 2015 model of diffusion, right? Since then, diffusion has come a long way. Um, like now there are ways to, as you're moving in your pathways, right? You could also give the model as input the class you want, right? And that class could guide the direction you take in latent space, or sorry, in image space, right? So that's one thing. Um, and then diffusion models early on were very slow because you need like 1,000 iterations to denoise an image, right? In modern day diffusion models, they've DDIM as opposed to DDPM, right? Instead of incrementally removing noise at every single step, they've found ways to do it much faster, right? Um, I won't get too much into it because it's like Markovian and stuff, but essentially with our diffusion models, right? Uh, we see the yeah, we see the previous image, right? So t minus one, and we predict image at t, right? So we only see the previous image essentially, right? And DDIM, right? So essentially same thing, but just faster denoising. They give the model more images, not just the previous images. So to go, for example, to go from like X3 to X2, we only see X2, right? Or wait, yeah, X2 from X3, right? We only see X3. In DDIM, we might see like X3, X4, X5, whatever, right? and they found that that's faster. Okay. That's really it. I low-key should have had slides for the last two things. My bad. But that's it. Any questions about diffusion as a whole? All right, I'm gonna take that as a no. So thank you for coming to probably my final lecture. I don't know, I might do like a guest lecture next semester.